У вас на 4-й и на 5-й группе микрофон выключен.
The most basic elements are atoms, or simple statements or simple propositions. Through atoms, we build up formulas. Then we use formulas to express various complex ideas. An atom is treated as a single unit. However, there are many ideas that cannot be treated in this simple way. For example, consider the following deduction of statements. Deductions at this is deduction. It is the proof of logical conclusion from given statements.
4-та, 5-та група вас не чує, якщо що.
Oh, really? Thank you. Oh my God. Just a moment. Oh my God, yes. Thank you. Thank you. Oh, what about now?
Yes,
Group
now
number 4 and 5, do you hear me? Uh-huh. Group 1, 2, 3 also. Very nice. So, for example, consider the following deduction of statements. every man is mortal. Mortal, смертный. Mortal.
We don't see screen.
You don't see what?
Number 45 groups can't see a screen.
Oh my God, just a moment. Ah, yeah, you're right. Because somehow it happened. Just a moment. Ага. Хан. Оп. Оп. Ага. Stop sharing. Now, once I ask you once again, groups 1, 2, 3. Do you see the screen? Lecture 9.
Of course.
Yes.
Just groups 4 and 5. Do you see lecture 9?
Yes. Yes.
Yes. That's why I'm waiting for the answer. So, example that shows that propositional logic is not sufficient for proving logical consequences or logical deduction in many cases. And simplest example, every man is mortal. Since Confucius is a man, he is mortal. The above reasoning here, so he is mortal. This we want to just prove that this conclusion is correct, true, or valid. The above reasoning is intuitively correct. Our intuition prompts us that this is a valid argument. However, if we denote by P the statement, every man is mortal. By Q, we denote Confucius is a man. By R, we denote Confucius is mortal. Then P and Q implies R is not a tautology. You remember, we said that for R to be a valid argument, for these three statements to be a valid argument, these are premises and these are conclusion. So this conclusion is valid only if this formula is a tautology. So is not a tautology. R is not a logical consequence of P and Q within the framework of propositional logic. This is because the structures of P, Q, and R are not used in the propositional logic. Not used. In this lecture, we shall discuss how the above argument, this argument, and similar arguments are proven to be valid in the first order logic. The first order logic has two additional logical notions compared to the propositional logic. Logical notions or concepts, or yes, compared to propositional logic. These notions are called predicates and quantifiers. Much of everyday and mathematical language can be symbolized by the first order logic. Now, what do we mean by a predicate? An n-place predicate is a function. So P is a function symbol of predicate function. x1, x2, xn are the arguments, and y is the value of the function. Where y, value of the function, is either true or false, and x1, x2, xn take their values in the set D capital or domain. It is set of domain, which consists of, in general case, of many elements, M. In general, more than 2. If we consider simple examples, two elements here will be enough to explain something, to show something, but the number of elements here may be 1,000 or maybe millions or something huge. D is a set of objects related to the situation under study. So here, set of objects related to the situation under study that we study. D is called the domain, or the domain of discourse. Discourse – это разговор, discussion, discourse. Every argument XI can be a variable, a constant, from here D, or a function. And what kind of function? With the arguments and the values in D. Function with arguments and the values in D. In the domain. In general, every exabyte may have its own domain, D sub I. To simplify our discussion, we shall assume one common domain for all arguments of one domain. Or if you like, we can just unite domains of each variables and get a common domain for all variables. But from the very beginning, to make it simple, yes, every variable take the values from the same set domain. Examples. Let the predicate great xy means x is greater than y, and x and y take their values from the set of two just elements, 1 to 3. So it is a small domain. Then greater 1, 3, 1 greater than 3 is false. Greater 3, 1, it is a true statement. So here we already have a statement presented by means of predicates, a predicate, and constants from the domain. Okay, true, greater to y. It is either false or true, depending on the value of y. Depending on the value of y. If y is 3, then it is false. Or y is 1, then it is true. Greater plus x comma y comma x. Again, look here. Greater, it is a predicate with the two arguments, first and second. The value of the first argument is given by the value of the function plus x plus 1. And this function x of plus of x1, it means x plus 1 greater than here x. This is what is denoted here. This function x plus 1 and here x. In the last example, this plus x and y is a function symbol for such a function, x plus y. So the value of the first argument is specified directly to the function, indirectly. We get it after calculating the value of the function, through the function value. Similarly, we can represent x loves y love with y by the predicate love xy. Love xy. Just a moment. Love xy. Then John loves Mary can be presented by predicate symbol love and its parameters John, love, John, Mary. Or John's father loves John can be symbolized as love, predicate, the first argument, father of John, and the second parameter, John. So this is how we can represent such a everyday English statement. John's father loves John by a predicate symbol love and the function father of X. Here, greater, love are predicate symbols. They are uppercase letters, PQR, or expressive strings. Greater, love, of uppercases. XY are variables. XY are variables. 1, 2, 3, John and Mary are individual symbols or constants. Plus and father are function symbols. And then place predicate P of X sub 1, X sub 2, and so on, X sub n is an atom. In other words, simplest formula. In the first order logic, atoms are connected by logical connectives. And here tilde that denotes not, and or, if and only if, which is equivalence, if then implication. So we use such logical connectives to build up formulas. In the first order logic, two special symbols are used to characterize variables. So here, so far, until now, we discussed what do we mean by predicates and how they are just created, constructed. But here, there are other concepts. In the first order logic, two special symbols are used to characterize variables. They are all, you see, upside down A, universal quantifier, and existential, just a moment. Existential quantifier. Now, this symbol is read for all x, or for each x, for every x. And this symbol is read, there exists an x, for some x, for at least one x, something is true. Look, what is true? Example, let P of x denote x is a prime number. Such a statement, x is a prime number. Qx denote x is a rational number. R of x denote x is a real number. Less x and y denote x is less than y. So these are predicate symbols. The following formulas denote such statements. So we shall make formulas of using these predicate symbols. For every x from Q of x, it follows R of x. Every rational number is a real number. This is how we can read this, or what is meant by this formula, if we understand the meaning of the predicate in this way. There exists x, a number x, which is a prime number. This is the statement denoted by this formula. For every x, there is y, such that such x is less than y. For every number x, there exists a number y, such that x is less than y. Now we understood how we can just present natural language statements using predicate symbols and quantifiers. But it's far from all about these concepts. The scope of a quantifier, the scope. Do you understand what is a scope? The scope, it is... Yes, область, да. Область, где действие этого кванта. Область действия кванта. In a formula is the part of the formula to which the quantifier applies. If a formula contains no brackets, then a quantifier is applied only to the nearest predicate on the right. So if no brackets, this quantifier is applicable only to Px. This quantifier is applicable to both predicates because we denote the scope by those opening and closing brackets. For example, the scope of both universal and the existential quantifier in this formula is less of xy. This formula. Only one predicate is the scope of both quantifiers. For there is x such that A or B, it stands for what is the scope of? There is at least one x. We put the brackets here, quantifier. This is the scope of this quantifier, includes only A, and B, it is not in the scope of this quantifier. That's why I put additional brackets here, and after that, just to show the beginning and the end of the formula. We have to distinguish between bound variables and free variables. Bound and free variables. Definition. An occurrence of a variable in a formula. Occurrence of a variable in a formula is bound if and only if the occurrence is within the scope of a quantifier with that variable, or is the occurrence in the quantifier. Occurrence. What do we mean by occurrence? It is a place where we find a variable. For example, here we have one occurrence of x in the quantifier itself and another occurrence of x. It is in the list of parameters of the predicate. Two occurrences. So I will just show you examples. The occurrence of a variable in a formula is bound. A current can be bound or free. Case bound if and only if the occurrence is within the scope of a quantifier, like here. With that variable or with the occurrence in that quantifier. Here. Occurrence in the quantifier, this. An occurrence of a variable, again, one place to find a variable in a formula is free if and only if this occurrence of the variable is not bound. Definition. A variable is free in a formula if at least one occurrence of it is free in the formula. So there can be many occurrences, several occurrences of a variable, if at least one is free, I mean outside the scope of a quantifier with that variable, then that variable is considered to be free in a formula. A variable is bound in a formula if at least one occurrence of it is bound. Now, finally, example. Here, not too much to read, but look, for all x, and the scope of this quantifier starts from here and finishes here. That's why both occurrences of x and x are within the scope of x. And these are bound occurrences of variable x. And bound occurrences, all occurrences are bound. X is bound in this formula. If all occurrences of x are bound, then x is a bound variable in the formula. Here, another example. For all x, a of x, or b of x, this occurrence is bound, this occurrence is bound, and this occurrence is free. So some occurrences are bound, some free. That's why we conclude x is a bound and free in this formula. Is bound and free in this formula. The truth value of a predicate does not depend on the bound variable. The truth value of a predicate does not depend on the bound variable. Meaning, a bound variable is a dummy variable. Dummy variable that looks like a variable, but actually is not a variable. It does not affect the value of the formula. The predicate value depends on the values of free variables, if any, on the domain D, and the meaning of the predicate. Let now some examples, just for us to understand why this, for example, variable x does not affect the value of the formula. And here, this x may affect it. Let even of x stands for x is an even number So predicate symbol and x. And less equal of xy denote x less or equal y. Then for every x, even x, actually it is, if we replace x by y, for every y, even y, it doesn't make any change. Is true. But if these variables x and y belong to the same domain, and the domain consists of only three numbers, 2, 6, and 10. So you take any value from here, and it is even. That is why it is true. Never mind how we what is the name of a variable. Never mind what is the value of the variable. Y, Z, Q, R doesn't matter. If we take consider, we don't even substitute. We look at the domain and see, here only all the elements are even. That's why such a predicate, universal predicate, is is true. For every x, even x, for every y, even y, it looks the same formula, same equality, but it will be the value of each of these things will be false. Here false, here false, here false, here false. They're equivalent but false. If my x and y, now I define the domain differently. 2, 5, and 7. No, not every x in this domain, not every element in this domain is even. That's why this is false and this is false. There exists even x, there exists y, even y is true, depending what are the values, what is the domain. There is even. So 3, 6, 8. Yes, there are 6 and 8 that are even. That's why we can find a value that brings 6, for example, or 8. It is true, and this is true. And here there is x, even x, which is actually the same statement. There is y, even y. It will be false if the domain will be 3, 7, 9, 11. All of them are odd numbers. None of them is even. That's why when we say there is some even number here, well, it is false. Here, for every x, sorry. There is x, there is y, less equal xy. It is same statement, but there is v, there is w, less equal vw. It is true if these variables x, y, v, w take their values in the set, such set 3, 7, 9, 11. For example, we take x equal 7. Y we can take 9. Then 7 less or equal 9 will be true. Never mind how we denote the variable, v or x, and so on. And here, for every x, there is y less equal xy. For every v, there is y, w. W less equal v w. It is true. It is true. If these variables x, y, v, and w take the values from 2, 6, 10, 2, 6, 10. Well, even if x is 10, y can be also 10 because equal. 10 less or equal 10, true. Here, also 10, 6, 6 less or equal 6, or 10. So there is no limit value here that makes it false. Note, formula containing three variables cannot be evaluated. May I ask you, oh my God, what have I done? Boy. Hi. People, in the groups number 1, 2, 3, do you see this, my lecture on the screen?
Yeah, we see. Yes.
In the groups 4 and 5, do you see it? Yeah, you too. Because, please, sometimes I first press the button and after that I find that, well, I stopped sharing. But I wanted to ask you, do you follow me? Do you understand what you do? If something, a word is not clear or something, just, you may just, I don't see your chat, but you may say, well, please explain something. I can return to it. Okay.
Скажите, вы, кажется, еще забыли запись включить.
Oh, really? We have now, people, do both of you, both groups, see the lecture on your screens?
Yes.
Yeah. Okay. Example. Translate this statement. Every man is mortal. Confucius is a man. Therefore, Confucius is mortal. Into a formula. Well, let us denote X is a man by man of X. X is mortal by mortal of X. Every man is mortal can be represented, look here. It is interesting. Every man is mortal. If X is man, then X is mortal. This is how we, rethink, interpret this simple statement, every man is mortal, into a formula. And after that, this every man, we use this universal quantifier. We denote Confucius is a man by man Confucius. And the whole statement can be now represented by such a formula. Now, we have two premises. For every x, man of x implies mortal x, one premise. And second premise, and this conclusion. And we know that if this implication is a tautology, then this is a valid, how to say, conclusion from these premises. Yes, but now we are not in a position to continue proving anything. Now we have to, by the way, people, I'm sorry, but let's have a break.
Okay, without problems.
Okay, we continue our efforts. I hope you're ready. I'm here. Interpretations of formulas in the first order logic. In the propositional logic, an interpretation is an assignment of truth values to atoms, truth values to propositional variables. In an interpretation of a first order logic formula, we have to specify such things: the domain of variables, and assignment of values to constants, functions, symbols, and predicate symbols occurring in the formula. So, example, once again, the domain and assignment of values to constants, if any, function symbols, predicate symbols occurring in the formula. Example, let us consider formula, two formulas, for all x, p of x, and another formula, there is x, not p of x. First of all, first we, in order to interpret and find the value of these functions, formulas, we choose the domain. Of course, in order to understand, we will choose the simplest one, 1, 2. Of course, we can, 3, 4, 5 or something, just much longer domain, but it will only make obscure the concept that we want to explain. Simplest domain, assignment for values of the predicate, for the predicate. So P of 1 is equal true, P of 2 is equal false. It is clear that for every x P of x is false in this interpretation, in this particular interpretation. Because P of x is not true for both x1 and x2. On the other hand, not P of x is true in this interpretation. In this interpretation, this formula is true. There is x P of 2. P of 2 is false, but not P of 2 is true in this interpretation. That is why there is x, not P of x, is true in this interpretation. Yes. Example. So we did not substitute any values into the formula. We just looked at the domain and just try to make a conclusion about the value of the formula. One more example. Consider the formula. For all x, there is y, such that P of x, y. With an interpretation, again, simplest. One domain, 1, 2. Now, P of 1, 1. We just here, P of 1, 2, P of 2, 1, P of 2, 2. Here it is standard. We have to list all possible combinations of values. And here it is our choice, whether it is true or false. Actually, not sure. Here we just chosen the value, let it be true, here let it be false. But in real life, we just watch what is the case in the real life and register it in the table. So True, false, false, true. If x is 1, there is y1 such that p of p1 y is true. If x is 2, there is y equal to 2 such that p of 2y is true. Therefore, in this interpretation, this formula is true. Definition. A formula G is a contradiction if and only if there exists no interpretation that brings value true to G. And I hope you understand that the number of these interpretations is infinite. We may increase the length, we can change the elements here in the domain, we can change the true and false values here, and especially if the domain will be longer, then it will be doubled to domain this table of assignment of values to predicates. But still, a contradiction if and only if there exists no interpretation that brings value true to formula G. Definition. G is a tautology if and only if for every interpretation of G this for G is true. This G is true. Also, how can we know that with any possible interpretation, which is infinitely, there are infinite number of interpretations, it is always true? This is the question that we leave now unanswered. Definition. A formula G is a logical consequence of formulas F1, Fn, if and only if, for every interpretation gamma. If F1 and F2 and so on, Fn, if this conjunction of these formulas is true, G is also true in this interpretation gamma. So for every interpretation gamma, whenever it is true, then G is also true in the same interpretation. Example. Consider formulas. F1, for all x, man of x implies mortal x of x, mortal x. F2, man of Confucius, therefore, formula G, mortal Confucius. Now we will prove that formula, mortal Confucius, is a logical consequence of F1 and F2. Yes, it will be not quite, how to say, mechanical proof, but for now, I want you to see that the proof will be by contradiction, by contradiction. Consider any interpretation gamma that brings true to these two, meaning that this for all x mortal x implies mortal x and man of Confucius, this formula is true. Certainly, if in this interpretation gamma if it is true, man Confucius is also true, because for this conjunction to be true, this must be true. Okay, it's true, right. Now, but let us assume that what we want to prove, mortal Confucius, is not true in this interpretation gamma. We assume that it is not true. We need to prove that it is true, but we assume that it be not true. Then, man Confucius implies mortal Confucius. We substitute here, instead of x and x, since it says for every x, well, why not Confucius? We put Confucius implies Confucius, and the value will be man Confucius true, because this is true, but mortal Confucius is false. But in this case, our formula, that is an implication, from true we get false, become false in this gamma. This means that for all x, man of Confucius implies mortal Confucius is false in this gamma, which is impossible because we assumed, we believe, and just take it for granted that both these two formulas are true. It's not true, so we get a contradiction to what we assumed from the beginning, and now is not true in this interpretation. Then man Confucius implies mortal Confucius is true, false equal false in gamma. I'm just sorry. Therefore, we came to conclusion that this premise cannot be true, but it is true. Therefore, mortal Confucius must be true in every interpretation that satisfies these two formulas. For all x, man of x implies mortal x, and man of Confucius. This means that mortal Confucius is a logical consequence of F1 and F2. We prove by contradiction. So at first we try to assume that it is false and came to the conclusion that this must be false also. But since we know from the beginning that these two formulas are true, then our contradiction appeared because of this, our assumption that this is false. This is false. That is why, if false, it doesn't suit this discourse, and if true, then everything's okay. In any interpretation, when both of these formulas are true, this must be also true. But it is somehow not quite a real formal proof. We'll come to a more machine-like methods of proving such implications that are used in knowledge-based systems, artificial intelligence systems, and so on. So we'll get an idea, a very, very general idea, how it is done. But now I want to remind you, sound rules of inference. So if these two are, this is true, and this is true, then B is true. It is modus ponens. Here, if this and this is both are true, then A and B are also true. If A and B are true, then A must be also true. And of course, B must be true. Double negation, unit, aha, here. Resolution method. If we have this premise A or B, and another premise not B, and if both of them are true, then A is true. A is true. It follows logically. And finally, if premise A or B is true, not B or C is also true, then A or C follows logically from these two premises. And this is, a rule is called the unit resolution, and here just the resolution. Few words about resolution, this method. Resolution is a valid inference rule producing a new clause, which is implied by two clauses containing complementary literals, complementary, B and not B. B and not B. These two clauses contain complementary literals, and these complementary literals disappear, and the remaining items are connected by or. Note, literal is an atomic symbol or its negation, like P and not P, and here B and not B. Amazingly, this is the only inference rule you need to build. The only inference rule you need to build a sound and complete theorem prover. It is based on contradiction and usually is called a resolution refutation. Refutation, actually, it is denial. Its synonym is denial. Denial of the what we try to assume that the opposite is the negation is true, and come to contradiction. That's why our assumption that it was false is wrong. The resolution rule was discovered by Alan Robinson, USA, University of Syracuse, in the mid-60s. It is a rather recent discovery in mathematical logic. Look, we at first for many centuries and even millenniums, people thought that all the rules of the logical thinking were discovered by Aristotle. No, something was added by John Boole. Was it John? Sorry. By Boole, English mathematician. But Alan Robinson added something which actually works with computers in middle of 60s. Note, formula G is a logical consequence of formulas F1, F2, Fn if conjunction of these formulas and implication of G is a tautology. Okay, this we know is nothing new. Is true under any interpretation. It works in propositional logic, but in the first order logic, a formula has an infinite number of interpretations. So it is impossible to check every interpretation. Yes, that's why this formula doesn't work for us. Formula G is a logical consequence of F1, F2, Fn. So this is a logical consequence. But if we take the negation of it, then it is always false. So we take negation, and after that, get rid of this implication. And it will be F1 and F2 and so on, Fn, and not G. This formula is a contradiction. It falls under every interpretation. And what is interesting, it is possible to detect a contradiction without considering all interpretations. Oh my God. No. Just a moment. A couple of minutes of rest. Because my vocal cords become strained and causes some pain. Okay. Basic steps for proving a conclusion G given premises F1 and F2. So given premises, and we assume that these premises are true. These premises are true, and we want to prove that G is also true under this interpretation. First, convert F1, F2, and not G to its Prenix normal form. Prenix normal form. Convert the matrix of the Prenix normal form to conjunctive normal form, where each disjunction, so what is conjunctive normal form? It is conjunction of disjunctions, where each disjunction is called a clause. Clause or sentence, clause. So this is step 1 and 2. Step 3, this is a loop. Repeat until contradiction or no progress is made. Select two clauses with complementary literals and call them parent clauses. Call them parent clauses. Resolve them together to produce a resolvent, performing all required unifications. You'll see what do we mean by unifications. If the resolvent is the empty clause, resolvent, result of resolution. Empty clause, like clause P and not P. It is an empty clause. An empty clause. Yes, I mean, after this, we take a literal and it's a clause with the complementary literal. After that, both of them disappear. We get an empty clause. A contradiction has been found because at this step, we put clauses that are supposed to be true. But now, if we come to such a situation, we come to a situation that we state P is true and not P is true. Of course, there is contradiction, and we spot it by obtaining empty clause. has been found, report conclusion. We report conclusion. G is a logical consequence of F1, Fn. So, meaning that this formula is always false, is always false. If not, add a resolvent, the result of this combining two apparent clauses to the premises and get repeated. And finally, step 4. If we did not succeed in step 3, we report G is not a logical consequence of F1, Fn. This is how. But in order to start using this algorithm that looks only so simple, but which is not quite that so, especially if the number of clauses in the database, the statements that were found to be true at the previous stages, is huge. So how to search for complementary clauses. So because we want our proof procedure to be fast. But we don't talk about it now. We just want we want to understand how to build Prenix normal form for such a formula. Definition. A formula F in the first order logic is said to be a Prenix normal form, PNF, if the formula F is in the form of, is presented by such a format of some predicate for variable x1, some predicate for variable x2, and so on, some predicate for variable xn, and here a formula without predicate, no, excuse me, why predicate? Quantifier. Sorry, quantifier for x1, quantifier for x2, we don't even say here, what is it, universal or existential. Just a moment. Quantifier for variable x, and later formula without quantifier, where q of I sub I xi is either xi with the universal quantifier or x sub I with the existential quantifier. And M is a formula containing no quantifier. Okay. This part of the formula is called the prefix of the formula F. M is called the matrix of the formula F. Here are some examples of the formulas in PNF. Look, here, for all x, for all y. After that, here we have a matrix P of xy and Q of y matrix. Here, for all x, for all y, not P of x implies Q of y. Another, because here matrix, no quantifiers, all the quantifiers here. And here, prefix, pre-quantifiers, and the formula. But how to transform how to transform correctly so that it does not, how to say, distort the logical meaning of the formula. We'll discuss it. In order to transform a formula into its pre-next normal form, we need basic pairs of equivalent formulas in first-order logic. First, formulas f and g are equivalent, denoted by f, these three parallel lines, horizontal lines, g or f equal g, if and only if that the truth values of f and g are the same under every interpretation. Okay. The basic pairs of equivalent formulas for propositional logic are true for the first order logic also. You remember idempotent, double negation, after that De Morgan laws, distributive laws. Yes, they are there. In addition, there are other pairs of equivalent formulas containing quantifiers. Now, in these formulas, f of x denote the formula f containing variable x. G denotes a formula without variable x, because here we don't show this parameter x. The following pairs of equivalent formulas are called laws. Laws in quotation marks. They are just useful pairs of equivalent formulas that can be conveniently used for transforming formulas. For example, for all x, f of x, or g, and g doesn't have any x. It is equivalent to for all x, and f of x and g are included in the scope of this quantifier. Same here. There is x, f of x, or g. Again, we include g into the scope of existential quantifier. So here about or, and here about and, g without x. So universal and existential, you can extend their scope or a formula or a predicate without variable x. Yes. Now, I'm so sorry. Okay, now not for all x, f of x. It is a common negation for quantify, and it is equivalent to there is some x for which not f of x is true. So kind of De Morgan law. Here, not there exists x, f of x. For all x, not f of x. если здесь не имеется таких x, значений x, для которых f of x есть true, так это же тогда естественно. Ну, так сказать, из этого следует, что для всех x не f of x это ложно. Так. Ну, here just I discuss briefly what actually I told you how to prove these equations. You will read it yourself. Now, next group of here, how many? 6 equalities. Now 2 more. For all x, f of x, and for all x, h of x, we can factorize, distribute for all x over conjunction. We put one common quantifier for both f of x and h of x. And next equation, which is true, there is x, f of x, or there is x, h of x. It is equivalent to there is x, f of x, or h of x. Okay. However, the universal quantifier and the existential quantifier can distribute over or and end respectively. So, look here, for all x, f of x, or for all x, h of x, it is not equivalent to for all x, f of x, or h of x. Meaning that there are some interpretations of this formula where this formula is true and this formula will be false. Okay, now same here. Existential quantifier over the same variable, and we cannot just move it before the brackets. There is x because it may be not always, these formulas not always have the same truth values. We can choose such a interpretation of f of x, h of x, so that, okay, here, example. Let us prove this, that this is not equal. f1, f of 1, it is true. F of 2, it is false. H of 1, let it be false. H of 2, it is true. Now, for all x, f of x, of course, false. For all x, h of x, it is also false. That is why we take disjunction of these two formulas. It must be also false. But this formula is true because for every x, we take x equal 1. Then now f of 1 is true, and here f of 1 is 0, but the 1 or 0, it is 1. We take 2, f of 2. Yes, f of 2 is false, but h of 2 is true. That's why 0, false and true, it will also true. For every x, this formula is true. That's why left is false formula, left side formula is false, and right side is true. Now, every bound variable is a dummy variable. Oh my God, is a dummy variable. It can be renamed. Suppose we choose a variable z that doesn't appear in f of x. Here, z doesn't appear. That's why, in this case, we just x here denoted by z. And after that, this formula doesn't contain x, so it can be moved. We move x here. And, well, it is moved in the scope of the quantifier for x. And after that, for every z, now here, this formula doesn't have z. We also include it into the scope of this quantifier by 318, by 318 as we, by this one. Okay, people, I ask you at home, at home, please read this lecture and the next lecture to the end at home. And after that, we'll very briefly and quickly finish it. Oh. Do you have any questions? I remind you, people. So in 110, we don't have a consultation. If anybody has questions, please join me at 3 o'clock. At 3 o'clock. And for now, I have 20 minutes for taking my pills and so on. Bye-bye. Bye.
Bye-bye.
Thank you. Bye.
Goodbye.
God bless you.
Stop sharing.
Bye.
Bye-bye.
Bye-bye.
See
Bye-bye.
you.
Bye.
Yeah.